Hello students. So today we are going to start with the topic conjugate beam method. Okay, so deflection of beams, calculation of slope and deflection of beams using conjugate beam method. So till previous class we have seen Moore's theorem, that is moment area method, then double integration method, Macaulay method. So these are the methods we have studied till now, and they were really good and efficient methods. But there comes a problem when for a particular beam, when its flexural rigidity is not constant throughout the beam. Okay, so whenever this ei value is mostly constant, whatever problems we have solved till now, but if it is changing, okay, if it is varying, then the conjugate beam method is really helpful. So let us start with the basic definition of the conjugate beam, what it is. So mostly conjugate beam method is used for the cantilevers and for prop cantilevers and other beams as well. So the slopes and deflection of a beam and cantilevers, it can be obtained by various methods as we have seen. The slope and deflections of such beams where EI is varying, we can use this conjugate beam method. So here, let us first define what is conjugate beam. So conjugate beam, it is an imaginary beam. Okay, it's an imaginary beam of length equal to that of the original beam. So it is an imaginary beam, but its length will be equal to. So this is a beam. Okay, this is suppose we are still in definition part only. So suppose this is some beam given, okay, some simply supported beam with subloading. So conjugate beam is actually, it's an imaginary beam. So we convert this into a conjugate beam, okay. So it is an imaginary beam and where length equal to that of the original beam. So here in this, you can see this is our original beam. This is original beam. Now, for this particular original beam with us load acting in the middle, we know that it's simply supported. For this simply supported beam, its bending moment diagram will be like this. Okay, so BMD will be like this. So from original beam, we convert it as a conjugate beam by considering its load diagram is M by EI diagram. Okay, so what I want to tell you, that with this simply supported beam, its bending moment diagram, first we have to draw. First step is to draw a bending moment diagram. So this is your BMT. Okay, bending moment diagram. Once we draw, then we divide that M by EI. We make it by M by EI. Okay, so here comes a third step. So this is your actually M, that is bending moment, M by EI diagram, and this becomes your conjugate beam. Okay, so the load diagram, because of this, the whatever bending moment, it becomes a loading for the new beam. So actually this is your conjugate beam. This is your conjugate beam. So just see the flow. From original beam, we draw bending moment diagram. Okay, and then for that bending moment diagram, whatever EI, okay, EI is a flexural rigidity. Now for this particular case, EI is constant throughout. So our EI, M by EI is like this. Okay, so this becomes our conjugate beam. Now suppose if this is RA for an original beam, suppose this is a beam AB and we calculate RA and RB, support reactions for this. Okay, now with this RA and RB, we calculate the bending moment. So again, now this bending moment diagram, actually it becomes our loading. Okay, this is our loading for the conjugate beam. This is our M by EI diagram. Now again we calculate reactions over here. So let us call them as RA star or RA dash, RB dash, as per our convenience. So this is the concept. Okay, so we first draw bending moment diagram and that bending moment becomes our conjugate beam. Now, how do we calculate slope and deflection from this conjugate beam? So once we get this, once we get this conjugate beam, then slope. Okay, so slope at any section. So any section. So for conjugate beam, slope at any section of the beam is equal to the shear force at the corresponding section. Okay, so shear force. So for this particular beam, whatever shear force, suppose I consider it as a section XX. So if I calculate shear force at this particular section XX, means that shear force is a slope for the original beam. Okay, so this says the slope at any given section of the beam is equal to shear force at the corresponding section of the conjugate beam. Shear force at conjugate beam. Okay, so shear force for this means slope for this. Okay, the original beam. So that is our first. You have to remember this. Now coming to the deflection. Okay, now what is deflection? So deflection at any section of the given beam is equal to the bending moment at the corresponding section of the conjugate beam. Corresponding section of the conjugate corresponding section of the conjugate beam. Okay, so when we construct a new conjugate beam, for this particular conjugate beam, slope and deflection we get by considering shear force and bending moment for the new beam. Okay, so conjugate beam is an imaginary beam and which help us to calculate what is the slope and deflection for a particular beam. Now let us solve this particular, consider this particular beam and let us calculate the slope and deflection for this particular beam. Okay, so here is our diagram. Let us name it. So this is our A, B, and load is acting at this. The span is L by 2. L by 2 means total span is L. Okay. So with this, we know that bending moment diagram will be like this, triangular. And the maximum bending, I hope now you remember. If you don't remember, quickly you should be able to draw it, calculate and draw. So it is PL by 4 or WL by 4. Okay. Now this is our bending moment diagram. So once we get bending moment diagram, then we are going to convert it into a conjugate beam. So by converting, considering this as a uniformly varying load. Okay, so this is the load acting. So this is actually our load diagram. Now this is this is M by EI diagram, right? This is our M maximum, WL by 4 EI. Let us name it as D star, C star. This is B, this is A. Now, as for this particular beam, load was simply, when it is W, it is W by 2, W by 2. And with this, when it is W by 2, this became W by, moment at this point is W by 2 into L by 2, WL by 4 we have written. Now we also need to calculate what are the reactions at this particular point. Okay, so let us calculate support reactions. So let us name it as RA star and RB star. Okay, so total load summation of, now again we will apply here summation of forces in y direction is 0. So total load acting is RA star plus RB star is equal to area of this whole triangle. Okay, area of the load diagram. So what is the area of the load diagram? That is 1 by 2 into AB into C star D star, C star D star. So 1 by 2 into AB is L into WL by 4EI. Okay, C star D star is WL by 4EI. So when we multiply, we get it as WL square by 8EI. Now, this is the reaction. RA star plus RB star is this what we have got. Now we know that the reaction at each support for the conjugate beam, this is the total load acting and it's a symmetrical triangle. So it will be half of the load taken by each support. Okay. So reaction at each support, that is RA star and RB star, will be same because it is a symmetrical triangle. Symmetrical triangle means the load acting is a same load is acting over here. So here we can simply divide it by 2. So half of, let us divide this load by 2. So make it half of it, half of WL square by 8EI. So WL square by 16EI is the support reaction. Okay. So RA star, RB star is WL square by 16EI. Now let us calculate what is theta A. So theta A is equal to slope at A for the given beam. Slope at A for the given beam. So what is the slope at A for the given beam? dy by dx at A, right? And what is yc? Yc is a deflection at C for the given beam. Deflection at C for the given beam. So according to conjugate beam method, theta A is a shear force at A for the conjugate beam. So according to conjugate beam method, theta A is equal to slope at A shear force at A for the conjugate beam, and that is shear force. What is shear force at A? So at A, if you see, shear force is nothing but only reaction. So that is RA star. So shear force at A is WL square by 16. So we have done with the slope. Okay, so simple, right? Very easy. Once you draw the conjugate beam, then answers is we get it easily. Now what is YC? Bending moment at C for the conjugate beam. Now what is bending moment at C? We have to calculate bending moment at this point. So what are the loads available at the left side? Just see the loads available. So there is a reaction available and this triangular load, right? So what is reaction? Moment about C if we are considering RA into L by 2. So let us consider this RA star into L by 2. This is going clockwise and this is going anti-clockwise. Minus area of triangle. Okay, the load of this triangle will consider it as the area of triangle and the CG distance. Okay, this CG will be somewhere here, so we also need this particular distance. Okay, that will be whatever distance this is, L by 2. So 1/3 of L by 2 it is. Okay, so let us write area of the triangle 1 by 2 into L by 2 into WL by 4EI. So area of the triangle into CG distance 1/3 of L by 2. This is 1/3. So when we substitute RA star is equal to WL square by 16EI. So when we multiply it, it will become 32EI. 32 EI minus WL cube by 96 EI. This LLL, it will make WL cube by 96 EI. Okay, so finally we get deflection as WL cube by 48 EI. Okay, so for such a simply supported beam, we have calculated what is the slope and deflection. So okay, I hope this case is clear to you. Now let's see one more case, that when a simply supported beam, suppose this load is not acting over here, this load is acting at some other place. So in that case, how it will be? So let's see, start with the next page. So if this is the case, so for such case, okay, when load is not acting in the middle of the simply supported beam. So if such a beam is there, let us call it as AB, and here this part is A and B. Let us draw the bending moment diagram. So bending moment will be maximum here where the load is acting. So this will be our bending moment diagram, and then we will calculate, we will draw our conjugate beam. Okay, so similar diagram will be there, M by EI diagram. Now here also in this question EI is constant, so bending moment, same bending moment diagram will be there here also. So this is our bending moment diagram, this is our conjugate beam. So what is the difference between these two diagrams? This is M, okay, and this is M by EI. Okay, and this is our load diagram. So because of this W load acting over here, we have to first calculate the reaction. So I will not spend time in calculating this reaction, these are very simple. This is nothing but, we have solved many questions, okay, similar. So this is WB by L and this is WA by L, okay. And this moment, what will be the moment at this point? Let us consider it as a point C, okay, and total span is L, okay. Right, total span. So a moment at this point, RA into A, RA into A, so WAB by L, okay, that will be our maximum moment, WAB by L. Then this M by EI will be nothing but WAB by EIL. Okay. Now here we have hole. Now this is not a symmetrical triangle like a previous case. Okay. We have to consider two different triangles over here. So it becomes little lengthy, but easy to understand. So let us consider these support reactions are as RA star and RB star. Let us make it as this is C dash, this is D dash, so this is C star, the height of it. Okay. Now let us calculate support reactions RA star and RB star. So what will be the support reaction? So let us consider moment about support A, and we also have to consider what is the summation of forces in y direction. So when we consider moment about support A, so support A, then what will be the load? So RB, load into perpendicular distance. Then we have to consider these two triangles. Okay, so we will divide this into two triangles. Let us consider this as a part 1. This is 2. So when we calculate moment about A, so I will write here only. Let us consider moment about A is 0. So I will write RB into total L, RB star into L, okay, anti-clockwise. So this is minus, or I can simply write it the other side, RB star into L, equals to now area of this triangle, okay, area of this triangle and CG distance. So for this particular triangle, CG distance will be here, okay. So the way this triangle is placed, CG will act here and this particular distance will be 2/3. This is a longer distance now, so we will write 2/3 of, this is A, 2/3 of A, okay. This will be 2/3 of A. And for this particular triangle, CG will appear here and this distance will be, so this is 1/3 of B, but we need this distance, right, because we are considering moment about this point. So we have to consider this as a CG distance. So this is, anyway, if we want to write down, this is 2/3 of B, this distance, and this will be 1/3 of B. So this 1/3 of B. So when we consider this particular triangle, so area of this triangle into CG distance. So this to this we have to write. So we will write A plus 1/3 of B, okay, for this triangle. And area of, for this particular triangle, we will consider area of the triangle, that is half into A into this height, that height is WAB by EIL into CG. CG is how much? 2/3 of A, okay. This is a 2/3 of this length. So now let's start writing it. So RB into L, then I am considering this triangle, second triangle first. So okay, let me just write this side. RB star into L is equal to load ACD into CG distance of ACD from A, okay. Load A star D star, or better, load A C star D star, that is area of triangle, into CG of that triangle from A, plus load means area of BC star D star into C star D star into CG distance. So here we'll write half of, what is area of this triangle? Half of AC star base into height. C star D star is its height. So this is area of the triangle, second triangle, okay, into 2/3 of is CG distance, AC star, that is A will write, plus half of BC star, area of this triangle, BC star into D star, half of BC star into C star D star, into, now we need CG distance. So AC plus 1/3 of BC star. So simply substitute all the values now. AC is nothing but A WAB by EIL into 2/3 of A plus 1/2. I have reached here, into B into WAB by EIL into A into B by 3. Okay, so when we make it simplify, okay, when we simplify it, so we arrive at RB star is equal to W into A divided by 6 EIL L square minus A square, okay. So once we get RB star, then we get RA star is equal to W into B by 6 EIL L square minus B square. Okay. So once we get the reaction, this is little lengthy calculation. So you should be just careful while considering CG. Otherwise, it's easy. So once we are done with the reactions. Now let us quickly calculate what is slope. So what is slope? Slope at A, that is theta A, is equal to shear force at A for the conjugate beam. Okay, theta at A is equal to shear force at A for the conjugate beam. So what is the shear force? So that is nothing but only RA star. Okay, RA star. So we will simply write this RA star value, that is WB by 6EI by 6EF into L square B squares. Okay, so we will write and we'll get the slope here. So the slope is nothing but, I will not rewrite it here because this is the same value we'll get here. Now what is the deflection? Deflection is nothing but bending moment at C. Bending moment at C for the conjugate. Now what is bending moment at point C? So what are the loads? Just see all the loads at the left side. So I can write, when I say bending moment here, so RA into A, okay, RA star into A minus, okay, this is clockwise, minus area of the triangle, minus half into area of this particular triangle. So what is that area of the triangle? Half into base into height. So half, what is the base? Base is nothing but A. Base into height is WAB by EIL into CG distance. CG distance only this much, and this is A by 3. A by 3. Okay. So when we solve these, we get YC is equal to WAB by 6 EIL L square minus B square minus A square. Okay. So for this case, this is the way we get the slope and deflection for the particular simply supported beam. Okay. So hope students, the definition, the concept of conjugate beam is clear to you in this class. So we have covered our definition or the concept, and our first case was when simply supported beam with a point load acting in the middle. We have seen that, and we have done this case where point load is not acting in the middle of the beam. Okay. So hope you understood, and thanks for listening.